So we are good, and it's Friday. Happy Friday. Almost the weekend, almost time to celebrate. Not quite yet. A little bit of OChem first, or to get the celebration going, we could say. The middle of chapter 18, test one will be next Friday, not today. Still have a whole week for it, but chapters 16 through 18. We'll be onto that. And we've been doing electrophilic aromatic substitution. So let's go to the overhead real quick. I think last time we did nitration, sulfonation, halogenation, and alkylation. I think we did the first four reactions. Today we'll do Friedelcrafts acylation. We'll put the ketones on the aromatic ring. We'll show you their versatility to put primary alkyl groups on there when we combine it with the reduction, the Clemenson or the Wolff-Kishner reaction. So there'll be a couple other peripheral reactions that we'll be covering: benzylic oxidation, benzylic bromination, and combining with a couple of reactions from 351, but not many. The main event, of course, is the 5 electrophilic aromatic substitution. But then we've got quickly here, after acylations, we'll do disubstitution, where we already have a group on benzene, and it can either be a donor group here to give ortho-para products, or it can be a withdrawing group that will give meta products. Okay, that's kind of the key thing. And we'll come back to this in a second. Disubstitution, when we have a functional group already on benzene, where does the next electrophile go? We're going to have to see that. Some are strongly activating, which makes the rate very fast for the second addition, and some are deactivating. Okay, so I'll have to look at that. But the activators generally give ortho-para products, and deactivators give meta products. But we'll have to figure out why. Okay, that'll be the tough thing here. All right, Tyler, let's go over to the board here and start out. A little bit of a review, we can say. So we've got Friedelcrafts alkylation with ethyl chloride and aluminum chloride, and we make the ethyl benzene product here. And that's fine, good yield here. Industrially, it actually uses the cheaper reagent, ethylene, with a protic acid and a Lewis acid. So you can imagine what's going on there. You're protonating, you're using the Lewis acid to actually activate the chloride off, making it even stronger protic acid. And then the benzene attacks, right, with the proton added on there to give ethyl benzene. Now I'm showing you this set of reactions for a purpose, to talk about the industrial synthesis of a very important compound, styrene, which has the alkene on the benzene. Now, that's used as a precursor to make polystyrene. And maybe you're aware of the famous industrialist John Huntsman, who made billions of dollars making polystyrene. In fact, he had the world's market for that and production to make this material. And it's actually using this as the first step. And then this is the second step, a zinc oxide catalyst with high heat. You actually drive off a molecule of H2, which you can use, and that makes the styrene. So don't worry about this reaction. It's a dehydrogenation reaction, we would say. Okay. For our class, we're going to do this two-step thing that we're a little more familiar with, maybe. We're going to do benzylic free radical bromination. You see, that will give us the intermediate bromo ethyl. And then what's t-butoxide going to do? What type of reaction is that from 351? Who can help us out? Do the elimination, the E2 elimination. Yeah, so the E2 here gives you then the product. Still a good yield and everything, but in industry on large scale, they do that two-step thing with the zinc oxide. Now this brings up the question, why not just put the thing directly on with an alkenyl chloride, right? Do the Friedelcrafts with the alkene, the chloroethylene, right? Conceptually, that would be better. Activate this, right? Draw that complex and have benzene attack here. But there's a problem. If this is sp2 now, an intermediate alkenyl cation like that, a carbocation, is not stabilized. That's not an allylic cation. That's perpendicular to that pi bond. And plus, an sp2 carbon chloride bond is stronger than an alkyl sp3 carbon chloride bond. So there's a couple factors here. And even if it was secondary like this, if there was an extra methyl group, actually the attack here would be even slower because of sterics, okay? Trying to get past these groups here. And again, it's sp2 hybridized, so it's a stronger bond. So we're limited for Friedelcrafts alkylation to sp3 for a couple different reasons. So you can see the direct synthesis. They don't use this in industry. Doesn't work, okay? It's alkylation followed by dehydrogenation. It's the actual thing. But we'll know it like this. We'll see toward the end of the chapter. Questions on that anyway? Maybe that catches your attention a little bit. These things are done on very large scale, very useful process here. Let's get into Friedelcrafts alkylation now. So here's the reaction. Let's look at now an acid chloride. Okay, we're going to be making aromatic ketones. This is our fifth reaction, right? Aluminum trichloride. We do that reaction, and we can get the aromatic ketone. So whatever is on the acid chloride, we call this a carboxylic acid chloride. It's made from the corresponding carboxylic acid that you're probably more familiar with, and then a reagent SOCl2 called thionyl chloride. Now don't worry about that reaction yet. We'll learn more about it coming up in a later chapter. Okay, thionyl chloride. So for right now, in this chapter and for this test, we're just using the acid chlorides directly. Okay, so how does it work? What's our mechanism here? Well, it's similar to all the other four mechanisms. What's the key thing we got to figure out here? If we want to, what's the electrophile? Okay, so you have an idea on the other four reactions already, right? We have some sort of electropositive group that has a positive charge associated with it. So the benzene electrons can come and attack that. But what is it here? Well, let's take the lone pair and dump them into our empty orbital here. That is a Lewis acid after all. And what do we get? We get the complex here. Don't forget about those formal charges on there. So that's just complexing the acid chloride. And now what can occur at that point? Well, you can think about, well, does benzene attack directly? No, this is an sp2 hybridized carbon. I just said the sp2, no direct attack. In fact, they're less reactive. But this is an unusual type of sp2 hybridized carbon in that it's got the lone pairs on oxygen right here. Plus, we can ionize this, right? It's a secondary position after all. So you might make that connection. But what do we get at this point? We'll get that with a plus charge, and then our chloride. Okay. And look at the plus charge right there. Okay. It's secondary, but it's on an sp2 carbon. That doesn't look too great. Is there any way we can make that a more stable cation? What does it have next door? Here, I'll give you a hint. What can we do to make that more stable? Resonance, okay. Yeah, someone was doing the curved arrow, I think, here. Very good. So let's bring the electrons down here and have a resonance structure. And it would look like this. Now that really looks funny, doesn't it? But this carbon here is neutral now, right? It has 4 bonds, count it up there. The positive charge is now an oxygen. There's just one lone pair left here. This is a funny looking cation. It's got a special name. It's called an acylium cation. Okay, acylium. Kind of a silly looking cation if you want to go that far. That's okay. That's the true electrophile though. And it's stabilized by resonance. Otherwise, you'd look at that and say, no, it's sp2. And inductively, it's next to an oxygen. That shouldn't be stabilizing. But look, resonance here. It does make it stabilizing. So it's known that once the Lewis acid coordinates, the chloride can ionize off. Okay, so it's a special case. And then what do? How do we get the product here? Well, we've done this before. If that's our true electrophile, we can attack either one, either resonance structure we can attack with benzene. And then what do we get? We'll get cation, and hydrogen's still there. That should look familiar, right? That's our intermediate allyl cation. And we've got stabilization here. We pulled these electrons out, right? We attacked here. Sorry, I flipped the ketone part around. But it's over here now. That hydrogen's still there. There's hydrogens on every carbon on the benzene. Then we get right here, and we're one step away from getting to the product. What do we need to do? Next step is what? Base, yeah. And what's our base? Down here, chloride. You take that off and then push the electrons back there. And you see you get back to the ketone product. Question on the mechanism? So the reactivity and the mechanism working there. The intermediate should look the same, should look familiar there. Okay, we can also do this reaction with anhydrides. We saw a couple variations of the Friedelcrafts alkylation. Here's a variation of the acylation, and it's using an anhydride. This is called acetic anhydride. It's actually acetic acid, two of them stuck together and water pulled out. That's why it's called an anhydride. So this is acetic anhydride. Sometimes we draw it like this. That means the same thing as that. You see the two acetyl groups on there. It's cheaper often in the smaller acyl groups for Friedelcrafts acylation are often these anhydrides. Okay, the acid chlorides can be made easily from any carboxylic acid, so you can make it, do the Friedelcrafts from any acid indirectly there with the thionyl chloride. But these are cheaper sometime and easier to use. You still need a Lewis acid though, so aluminum trichloride, and in this case, you get this molecule, which is the acetyl group going on there. That has a name, right? That's one of your parent names for the benzene nomenclature. Which one is this? This is what? Yeah. Acetophenone. Yeah, I'm not going to draw it out, but a couple people got it there. Yeah, so that's how acetophenone is made. You could make it from the anhydride or the acetyl chloride, right? But like I said, the anhydride is often cheaper. Well, how does this work? Well, it's similar. Let's coordinate a lone pair here into the empty orbital. And what do we get here? Aluminum chloride. Okay. And we need to break a bond here to get our acylium ion. So just one of the carbonyls of the anhydride gets on there. We waste part of it. Part of it becomes acetic acid at the end. I'll show you that. So what's the result of this? We're breaking this bond, pushing electrons up to make that neutral. You see we'll have acylium ion, and we'll have the aluminum acetate stuck on there. Okay. So acylium ion, that's where benzene does its thing to get on there, right? I think you can do the rest of that mechanism. What happens to the other part of the anhydride? Well, once you quench it or work it up with water, the water can be a proton donor for the acetate part, and you get a molecule of acetic acid. Okay? So it is a little milder. Before we got molecules of HCl as a byproduct. Don't worry about that. Okay, the business end is right here. Acylium ion again, and then Friedelcrafts acylation. going on there. Okay, questions on that so far? All right, let's look at another problem here. So we want to make reactions versatile, right? We want to be able to make certain types of compounds. So maybe we're looking at this in a little different way. Remember, we looked at Friedelcrafts alkylation before. And let's say we want to make this straight chain butyl benzene. Okay. Now there's a problem here. If we do Friedelcrafts alkylation with aluminum chloride, that might seem to be the way to make that, right? But what's the problem here? This will not give that. This is a primary position. When it coordinates, it'll do that shift, remember? And what will be the product instead in this case? So this is a little review from last time. It'll actually be the secondary butyl product being major. Okay. Only a very small amount of the desired thing is made. So how are we going to make this thing here? Well, we're going to do it a little bit different. We're going to take the corresponding acid chloride that has 4 carbons. Okay. We're going to do a Friedelcrafts acylation instead, and that'll be very good. Okay. We'll get the acylium ion on there. And by the acylium ions are resonance stabilized, so they don't undergo the rearrangements, okay? They're resonance stabilized at a secondary spot. They stay right there. No rearrangements on acylation. Alkylation, yeah, we see these rearrangements because it's carbocation stuff. But here we can get the ketone. 1, 2, 3, 4. Make sure you count carbons carefully. And then what? How do we get from here over to here? Okay, so here's the new thing. This we can use zinc, amalgam. Amalgam or amalgamation means adding in some mercury. The mercury makes the zinc metal a little more reactive. And HCl conditions, that's called the Clemmensen reduction. In fact, you can just say Clem by it, or the reagents are simple enough, zinc, mercury, HCl. And that will take the aromatic ketone directly to the primary product, okay, which we couldn't make before. We couldn't make that with Friedelcrafts alkylation. We had to go indirectly from the ketone and then do that. Or we can do what's called the Wolff-Kishner reaction. And this uses hydrazine, which is a very reactive molecule, 2 ammonia groups stuck together, hydrazine. It's actually used in rocket fuel. It's a strong reagent. And base, so KOH. So both of these are kind of a mouthful, either the Clemmensen or the Wolff-Kishner, and you can abbreviate it on a quiz or a test. You can just say Clem or WK if you want. But know what are in those reagents. It's nice we have the 2 reagents. One is acidic conditions, one is under basic conditions. If there are other sensitive functional groups in the molecule that can't tolerate base, we'll use the Clemmensen instead. If there's a acid-sensitive molecule in the functional group in the molecule, we'll switch over to the Wolff-Kishner instead. Okay, but that's reliable. No rearrangements at that point, and no mechanism needed here. You're off the hook. It's Friday after all. I don't want to give you yet another mechanism. There are known mechanisms for those reactions, but you don't need to know for this class. Okay. Sometimes we draw the line and we say enough is enough, right? And yeah, it's not in your book, the mechanism, so we won't put that on a quiz or a test. So don't ask me later, will the mechanism of the Wolff-Kishner be on test 1? No, it will not. Okay, we'll see. Hopefully that'll help you out there. All right, now let's back up even more and do some synthesis problems with these reactions. So, can we make this molecule? How do we make that one? How do we make this one? And how do we make this one? using any reagents you need. Friedelcrafts alkylation, Friedelcrafts acylation, followed by the reduction of the ketone, or what? First thing to analyze is what's the position here with an isopropyl group? It's secondary, right? What's the nature of the carbon directly attached on this one? It's primary, right? How about here? Yeah, primary again. So what are we going to have to do? We can do what? Friedelcrafts alkylation or acylation here if it's secondary. Which one would be most efficient? It would be a one-step reaction. Which one would it be? It'd be the what? Acylation or alkylation? Alkylation, yeah. And so that would be an easier one. We'd just have benzene, and we'd have isopropyl chloride and aluminum chloride. Yeah, that would give a good yield for cumene, isopropyl benzene. What about this one, though? Can we do Friedelcrafts alkylation here? No, that would rearrange, and it's branch, too. We'd get tert-butyl benzene. So what do we have to do here? We have to start with benzene, and we have to do Friedelcrafts acylation. And that, you see, will give us the aromatic ketone with the isopropyl group as our product. Okay, so that's acylation with the acid chloride. And then we can do Wolff-Kishner or Clemenson. Okay, pick your favorite one. If you like rocket fuel, you want to draw hydrazine and base, that's fine there. Or zinc amalgam HCl for the Clemenson. And that will take this off. It'll add in the two hydrogens for that primary position. If you want another mechanism, I can show you that later, but it won't be on our quiz or test. What about this one? Also primary. So what are we going to have to start with? Benzene again, but we're going to have to start with this acid chloride. And, you know, count up your carbons. Make sure you got 1, 2 carbons here and the cyclohexyl. So 1, 2 there, right? So that will give you your acylation product. And then Wolff-Kishner or Clemenson again, right? Okay. So already kind of helping you plan some synthetic procedures here. All right, let's look at dye substitution now. So we know how to put on all these great functional groups. We've got our 5 key reactions to do electrophilic aromatic substitution. But now we're going to say, okay, we've got a group on there, and whatever functional group that is, we want to add another electrophile. Okay. Do one of those 5 reactions again on whatever we've already got there to give a dye substitute product. And that next electrophile can either go on where? Ortho? Okay. Or where? 3 other spots, right? Meta? Or yet another. Is there a 4th? No. Luckily, that's the end of the road. If we try to go over here, that's the same as meta, right? So we got ortho, para, and meta possibilities here. So we've got to figure some things out here. If this functional group is an electron donor, and by donor, we mean it has a pair of electrons on it. So if it's like an oxygen or a nitrogen, and that's right on the carbon, okay? So this X group has to be right on there if we're talking about that. Or it's an alkyl group, okay? Those are electron releasing another carbon there, okay? If we have the functional group that's an electron withdrawing group here for this functional group, and that will be a couple different things, nitro, or if it's an acyl group, if it's got the carbonyl on there, and we'll see some others there as well. Those can be deactivating. If it's an electron donor group, it'll generally give ortho-para products. Okay. If it's an electron withdrawing group, a deactivator, it'll give meta products. Okay. So we got a couple of options there. Let's begin to figure out what's going on here. So if it is an X group, you see, by resonance then, that lone pair can donate into the benzene, make the benzene more electron rich. Because remember, the benzene is our nucleophile. It's reacting with the electrophile. So if this is a donor group, by resonance, it's making the benzene more electron rich. And it actually activates the ortho and the para positions. We'll see that with resonance structures. We'll have to examine those resonance structures there. Let's see, if it's an R group, you see on the benzene, inductively, that's donating because the carbons on the benzene are sp2 hybridized. They have more S character. There's less S character in the alkyl groups. So inductively, these are electron releasing, which again makes the benzene more electron rich and more able to react with an electrophile. So resonance effects and inductive effects can make it more electron rich. Now let's look at the withdrawing groups. Now an X group through the sigma bond though is actually inductively electron withdrawing. Oxygen and nitrogen are more electronegative than carbon. So through this sigma bond, they're actually pulling electron density out. But with an X group, an oxygen or a nitrogen with a lone pair there, this one dominates. The resonance effect is the more important one. Even though you have this deactivation going on, okay? They're working against each other. We'll have to look at that in a little more detail. But if you have halides, for example, the inductive effect dominates. They'll react slower, but notice halo groups still have lone pairs on them. So these halo groups will still be ortho-para directed. So I'm kind of giving you the bottom line, and there's some complicated issues here. But things like carbonyls, if they're directly on here, you see we have the partial positive. And we can draw a resonance structure. What? These are resonance deactivators. Okay? And that's what we talked about here. These are withdrawing groups, okay? So resonance can either be pulling electron density out. You see the oxygen here is 2 atoms away. Whereas if the oxygen's right on there, if it's a phenol type thing or an anisole, an ether right on there, that'll be an ortho-para director. But carbonyls are meta-directors, deactivating. Okay. If you're thoroughly confused, don't worry. We're going to look at specific examples, and hopefully this will make some sense here. In fact, let's see. Let's go up to the overhead there again, Tyler, and look through that just before we get going here. But we'll look at these factors in detail, of course. But here they are, the chart. If we have heteroatoms, nitrogen or oxygen, or amides or esters, those have the nitrogen, oxygens with lone pairs right next to the benzene. These are all electron releasing by resonance, okay? Those lone pairs can donate in and stabilize the benzene and make it more electron rich. And so those will react faster. These will direct to the ortho-para position. Deactivators, here's the inductively deactivating through the sigma bond, the halogens, okay? They will make things slower. They still direct ortho-para though, because of the lone pair resonance donation but it's balanced there. Okay, they're competing with each other. Then the carbonyls, anything carbonyl-wise, ketones, aldehydes, esters, amides, where the carbonyl is switched around and it's directly on the benzene ring. Those are deactivators meta. Cyanides, sulfonic acid, trifluoro or fluorinated alkyl. Those are strong inductive withdrawing groups like 3-fluorine. Those will also be meta. And then an ammonium cation. If you protonate aniline, do it under acidic conditions. In fact, when we do nitration or sulfonation of aniline, those strong acids protonate the aniline, make the cation. then the cation becomes a meta-director. So aniline, with some of the reactions, is a ortho-para-director. Under the acidic conditions, anilines or amines become meta-director. So again, you got to inspect the conditions and think about structure. That's the only way to keep track of these. And then nitro always has a plus charge on that nitrogen, so that's a strong deactivator. Okay, meta-director. All right, this chart will make more sense after we do some specific examples, okay? Let's get into the data here, and hopefully this will help us out. So I'm going to go through a series of reactions with you. First, we'll look at the kinetics and then the selectivity of them, but we're going to have toluene and trifluorotoluene, and we'll relate that to the reactivity of benzene. Toluene will react faster than benzene, and the slowest one in this series will be trifluorotoluene. And we're going to do nitration, all of them with what? Nitric acid and sulfuric acid. What's the true electrophile for nitration? Anybody remember it? Remember, went through the mechanism, came up with the true electrophile? Let's just have that up here. Nitric acid, sulfuric acid, what do they form? Remember the name of it? Look at your notes. What's the true electrophile? Water? Nitronium cation, yeah. So NO2, yeah. So that's what's going on. So we're nitrating all of these, right? And let's see. The relative rate. The relative rate here is normalized to 1. This is the slowest one. This will take 12 hours at 120 degrees. You have to heat that up a lot to get this one to go in a reasonable time. This one is 40,000 times faster than trifluorotoluene, and then the relative rate of this one is 1,000,000 times faster. Okay, so and this one will give ortho-para products major, and this one will give the meta product major. So let's look at the data. Let's take toluene, NO2, and we're going to get ortho, 63%. And I'll give you the actual numbers for these experiments first. And we get some meta product. But look, it's only 3%. And we get, and that's 34%. Okay. And let's see, the reaction is done in 30 minutes at room temperature. Okay. 63, 30, 34. Let's get the data up there for trifluoro. And you'll see the difference, right? With trifluoro here, it takes, well, I already got it up there, 12 hours, whatever. Okay, so it's very slow. And what's the distribution of products here? Oh, I got it on the other page. Okay. It gives some ortho. But again, it's CF3, okay? So it's different functional group that's on there already. And this one is 6%, okay? Meta is 91, okay? Remember the nitro groups on there now? We got 2 functional groups on there, right? And what's the other one? Paranitro trifluorotoluene, and that's only 3%. So what are we affecting? We're affecting, obviously, the rate. The more electron-rich methyl group, CH3, reacts very quickly, and it gives ortho-para products selectively. Okay? Tiny amount of meta. We can ignore that, actually. The trifluoromethyl is mainly meta product, okay? But it's very, very slow, inductively withdrawing there. All right, now let's try to figure this out. Let's go to the toluene data here and try to figure out why toluene is orthopara directing. And we're going to put on our nitronium group on a couple different spots, okay? So you have to follow along, you have to go through this to really know the why of orthopara versus meta-directors. If you don't draw out these resonance structures, you're going to struggle on the test of the quiz. So everybody's got their pencil ready to go. You might get a cramp in your hand here in a minute. Well, let's go ahead and do what? CH3. So we're doing the ortho pathway, okay? So let's see. So there's our cation, right? And the key here now is drawing the resonance structures. Let's push the electrons over here. And we got that one. Okay. And we got this one. This before we're taking off the proton, right? So these are resonance structures of our intermediate allyl cation. What do you notice here of these? Let's see. What's the nature of this cation? Just localized here. What is it? Secondary, primary, tertiary? Secondary. What about that one? Secondary? Ah, what about that one? Tertiary. Ah, that turns out to be the key. Because let's consider now the meta pathway. So if we pull the electrons out here, the nitro there, we're going to have that. Okay, then that's just putting the nitronium here, okay? So we'll have the cation here, okay? And which one is that? That's secondary. And draw the resonance structure. Oops, you get this one? Yeah. Also secondary. And what do we get? The next one, secondary down there. Okay. So the meta pathway, look, secondary, secondary, secondary. Ah, which pathway looks better already? The ortho pathway, okay? The meta pathway, putting the new electrophile at this position relative to the group that's already on there, makes so the cation's here, here, or here. It's never right there. But that's where we want it if it's going to fully bear out that electron donation, stabilization, right? Well, let's do the experiment. The last one for the para pathway, right? We'll have this down here. And yeah, I guess we got to put our cation in there. So that's using this bond here. Okay, go on there. That'll give us this, right? And the cation can be here. Or where? It can be right there. Or it can be down here. Now, all of these lead to their products, you know, after you take the proton off with the base. You can do them from any resonance structure, okay? Take that off. That'll give the meta product. This gives the ortho meta. Taking the proton off any of these gives us the para product. Okay, so what do we have here? Secondary. Ah, what do you notice there for the para pathway? Tertiary again, right? Yeah, so that's the good one. Secondary here. So the two good ones are right here. Tertiary and tertiary there. And notice that's for what pathway? Ortho and para. Okay. One quick question here. Why so much ortho? 63%. It's about 2 to 1 over para. That's just a statistical thing. There's 2 ortho positions in this molecule. And the methyl group's small enough, it doesn't matter. For the purposes of synthesis, when you can make either the ortho or the para, you can just make that. This one has a higher melting point, and you can selectively crystallize that one out and purify them easily. They're constitutional isomers, so they have different properties. You can easily separate them, okay, based on the number of things, melting point or boiling point. So ortho-para can always be separated, but you're not going to get any meta product from this pathway, okay? Why? Because this is a donor, and this pathway will have the lower stabilized allyl cation. This one, 5 to 10 kcals per mole, more favorable, this pathway. So the transition state leading to the ortho and the para products is going to be lower and more favorable, okay? Now, let's see if we can do the trifluoromethyl, right? We've got trifluoromethyl, and that one's going to give us the meta product. And we can analyze the same thing here. We've got trifluoromethyl now, and we've got our nitro. And yeah, let's just do all the same ones. But again, it's trifluoro now, right? So we'll have secondary here, and we'll have what? Secondary here. And look, let's just jump ahead to this one, and we'll have tertiary. Remember, we said that's good in this case, at least with the toluene, leading to the ortho product. So tertiary there. But notice that carbocation is right next door to the 3 fluorides. And those are all strong dipole moments, which makes this carbon much more positive in this case, right? So that'll turn out to be a bad thing to have it right next door to that deactivating group. Let's see, what's the pathway here? Meta. Let's get the meta one on there. So if we do the NO2 here, we'll have plus charge there, and there. So where will be our resonance structures here? Right there, right here. So secondary, and oh, where's the other one? Secondary right there. When we do the meta pathway and lead to the meta product, we never put the plus charge directly next to the withdrawing group, okay? So by having it go this meta pathway, it's a slow reaction. The trifluoromethyl is deactivating all the positions, but it's deactivating the meta pathway to a less extent than the ortho and the para pathways. It's strongly deactivating the ortho and the para pathway because that puts the plus charge right there. Let's look at the para pathway and see what that is, right? NO2. And you see, you'll have your electrophile in there. Cation will be here, secondary. Tertiary, that's the bad one right next to it. And then secondary here. Let's draw that tertiary one again. And you'll see it's the same as the ortho pathway, right? We're putting that plus charge right on there, leading to the para product. And that's the bad combination. We want to avoid that, just like here, okay? But notice the para pathway, or the meta pathway, hopefully I'm not misspeaking here. If we put the electrophile on the meta position, the cation will be here, here, and here. It avoids placement next to the withdrawing group, okay? So the deactivators will be forming the meta products to a greater extent than the ortho and the para positions if it's a deactivator. Questions on that? Let's see, we got both of them up here now. Let's look at both of them. So we've got toluene giving selectively ortho and para products, remember? What was it, like 60, 30%, and a tiny amount, trace amount of meta in that case. It's because in this case, the methyl group is a donor, inductively helping to stabilize things, being a CH3 group, and a tertiary carbocation in the localized allyl cation structure is beneficial. Okay, and so we get more ortho para product over meta. Because the meta pathway, we never put the plus charge right here to make it tertiary. It's always secondary. Okay, now it's activating all the positions. Actually, it's just activating because of resonance selectively the ortho and the para positions over meta. It's a fast reaction. Okay. Whereas with trifluoromethylbenzene, just having those 3 fluorides on there, now we switch it over to the meta product, and that's because the intermediate cation never puts the plus charge directly adjacent to the strong inductive withdrawer, the CHF3. Okay? Does that make sense? You can only see it if you draw it out and begin to think about that. Let me give you one to think about for next time. We'll go through the rest of the directors. We'll go back to the chart next time. But how about this one? So we can do this. Actually, phenol and is such a strong donor. We can kind of see where it's going to go, right? Here's our NO2. Let's just go right to it. You can see from that ortho position, you can put that NO2 group directly on there, right? And you know, to go to the product here, you need to use base to go to the phenol product, and it will favor ortho. And see if you can draw the resonance structure intermediate for forming the para product. Okay, and it'll be a similar thing. You'll just keep pushing the electrons down, and then use these to attack here. But the meta pathway, you can't draw a resonance structure. In fact, there's no meta in this case. This one's 44% ortho, and this one's 56% para. 0% meta. Because that pathway doesn't use the resonance effect of the phenol at all. Okay. So there you can kind of see it, right? And that would be as if when we pull that out, we'd have a cation right there, and we're just going ahead and doing the resonance right away, right? And then with base, then we're taking that proton off and then giving the phenol back, okay, the OH back. So phenol is a very strong activator, and it gives ortho-para products, okay? So that's the bottom line on that one. And we are out of time. Sorry about that. And sorry about our little delay getting started today. So very good. Have a good weekend. Be right up through the rest of the chapter. And we'll do the rest of the groups, and we'll do some multi-substituted benzenes next week and some synthesis problems as well. So we'll have that ready to go for next week. Okay, very good. See you next time. Thank you.